All right, we're all set.
Cool. Um, Hi everyone. So today I'll be presenting uh, the couple of new algorithms that we designed to make Sumcheck run faster over small characteristic fields. Um, I'm going to share some exciting results specifically over binary tower fields, but our techniques also apply more generally. Um, Also, this is joint work with Yuval, my colleague from Ingonyama, and Justin Thaler from E16Z and Georgetown University. So let's get started. So in the recent times, we have had new snark protocols that we have seen. For example, Binius, which enables efficient snarks over binary tower fields. Now, why do we care about uh, snarks over binary fields? That's a separate topic, but it's if I have to summarize, it basically enables um, us to work with bits or uh, break down your snark computation in bits, which is more natural for computer hardware to handle. So therefore it's Binius is one of these new snarks, new commitment schemes that enables these snarks, which has some promising results when we try to traditional hashes like Keccak and um, Grostel. So Binius basically is a very fast commitment scheme, uh, specifically for binary tower fields, and it's the IOP that it uses along with the commitment scheme is the Sumcheck protocol. Now, what ends up becoming is the commitment part becomes so fast that the Sumcheck part of your protocol, the IOP part of your protocol, now starts becoming a bottleneck. Because typically, if you would expect that Sumcheck being a linear time protocol, um, also Sumcheck involves only field operations, so it should never become bottleneck in snarks. But with Binius, the commitment scheme part is so fast that Sumcheck now becomes the bottleneck. So this is a screen grab from one of the presentations in ZK Summit 12, where the irreducible team presented some results on Binius. And we can see when they profiled Binius, the majority part of the proof function is now consumed by the Sumcheck protocol. So batch proof is basically like one Sumcheck call that does a batch Sumcheck instantiation. And if we zoom in a bit, we can see that this part is almost sort of capturing 2/3 or more part of the prover. So now Sumcheck has now become the new bottleneck. So the objective of our paper was if we can speed up Sumcheck, um, especially in these cases where Binius is used, that would allow us to make Sumcheck not be the bottleneck and improve the overall efficiency of the prover. Now we'll sort of go over a bit on why we care about Sumcheck over binary fields, or uh, we'll try to answer the question of why exactly Sumcheck starts becoming a bottleneck with these binary tower fields. So this would be a bit of a primer um, on binary fields. So as I said, we are going to focus on the case of binary fields in this talk, uh, and we'll discuss a bit about generalizations of our algorithms later. So binary fields are characteristic to fields of the form gf2 to the power n. So when n is equal to 1, we get the simplest binary field, just 0 and 1. And this is indeed a field because in which you can define the addition operation, the multiplication operation, and addition. Because this is just 1 bit, the addition is just simply XOR, and multiplication is just bitwise AND. Of course, we are interested in slightly larger fields as well, which we get by extending the base field. So if we consider n equal to 2, the field gf2 to the power 2 is a degree 2 extension of the base field gf2. Now, I'll not go into explaining the extension fields, but just to give a very brief idea of how we generate this gf2 to the power 2, whenever we need an extension field, we define something called as an irreducible polynomial. In this case, we define it to be x squared plus x plus 1. And then we say any polynomial that we define over our base field, which is just 0 and 1, when divided by the irreducible polynomial, should give us one of these remainders, right? It should give 0x plus 1, 0x plus 0, and so on. So therefore, what ends up happening is you can see that we started with the base field gf2, which contains 0 and 1. But now in gf2 to the power 2, we get pairs of these base field elements. So 0, 0 is a pair, 0, 1 is a pair, 1, 0 is a pair, and 1, 1 is a pair. So therefore, binary tower fields, or these extensions of binary field, give us a nice compact representation. Now, coming back to the sum check that is being used as IOP in the Binius paper, we see that the sum check is there's a base field, which is the smaller field or small characteristic field, and the witness of your snark is from the base field. But the challenge is from the extension field. So when you apply Fiat Shamir and sample challenges, the challenge needs to be sampled from the larger field, which is extension field. In this case, it's the GF2 to the power 128 extension field. The reason for choosing 128 degree 128 extension is to ensure we have a certain level of security, computational security for the given snark, which I'll not discuss. But the point here is the challenges are sampled from the extension field, which is a very large field. Now, if we run the Sumcheck protocol naively, without any optimizations, this would lead us to lots of extension field multiplications. And by running Sumcheck, I'm talking about the case when we run a product Sumcheck. So in product Sumcheck, you basically take a product of multiple multilinear polynomials, and what you want to prove is the sum of this product polynomial is equal to some value over the Boolean hypercube. So in specifically when you deal with this products of polynomials, you are going to end up with a lot of extension field multiplications, and we'll see why we end up with lots of extension field multiplications. When I discuss the when I sort of write down an example of how a product sum check looks like. Um, but if we assume that this is true, what this leads to is lots of extension field multiplications. Now, a natural question is, why is extension field multiplications so bad for us? And that's what we'll try to tackle next, which is multiplication in binary tower fields. I'll pause for a moment, just in case if there's questions. But if not, we'll proceed. So in binary tower fields, as we just defined, what we do is we start with a base field, let's say GF2, and we keep taking degree 2 extensions of our base field. So therefore, we end up with GF2 to the power 2. Again, we take degree 2 extension, and so on and so forth. And that's how you can get to GF2 to the power 128. Now, as I mentioned briefly, that there's a nice structure on how you represent the elements in these fields. And that's the and we'll see, uh, even though we have this nice kind of structure, why do multiplication in binary tower fields become expensive? So GF2 obviously has just two elements, 0 and 1. GF2 to the power 2, as I briefly mentioned, has 4 elements. Similarly, GF2 to the power 4 is going to have 16 elements. And these 16 elements can be represented as 4-bit numbers. So you can see we start from all 4 bits to be 0, all the way up to all 4 bits being 1. So this is the representation that I was talking about, that numbers in your binary tower fields can be represented using this compact representation. And if we take a careful look at, let's say, any element from GF2 to the power 8, so if we take a look at this number, 1, then 0, 0, 0, 1, 1, 0, 1, we can see that it's, of course, it's an 8-bit number because we sample this number from GF2 to the power 8. Now, what we are interested in is seeing uh, how we can uh, how we can represent an element from a larger field by breaking it down into element from smaller field. For example, if we take this particular element from GF2 to the power 8, we can break it down into 2 elements from GF2 to the power 4. Right. So if we take the first 4 bits and the last 4 bits, we can map them to 2 different elements from the previous field. We can repeat the same process and again break down the elements of GF2 to the power 4 into 2 elements of GF2 to the power 2. And we can keep doing this process until we have reached, let's say, GF2 or whatever field you want to stop at, whatever small field you want to stop at. So what that essentially means is there's a recursive structure in how you can break down elements from a larger field, larger extension field, into a smaller extension field, or even the base field GF2. Now, addition of 2 elements in any of these extension fields is pretty straightforward because you just need to take the bitwise XOR. So if you want to add 2 elements from GF2 to the power 8, you just need to take 8 bitwise XOR, which you can also pretty easily parallelize. What about multiplication? That's what we are more concerned about. So for multiplication, the recursive structure that I mentioned before is going to uh, come to our help. So what do I mean by that? So let's say if you want to multiply two elements A and B from, let's say, GF2 to the power 8, what you can do is you can break down each of those elements into lower part and higher part, just like I showed for the example from 2 to the power 8. Now, let's say A and B were from GF 2 to the power 2. So let's say A and B was just 2-bit elements. So in case of 2-bit elements, when you split the two elements, AH, AL, BH, and BL are going to be just 1-bit elements. And now if you open this multiplication, um, if you just naively like multiply these two brackets, you're going to get four multiplications, uh, namely AH times BH, AH times BL, AL times BH, and AL times BL. So therefore, you can compute a multiplication GF2 to the power 2 using four multiplications from the uh, 2-bit field, sorry, 1-bit field. Now you can use the same idea to multiply two elements from an even larger field by recursively breaking it down, breaking the multiplication down into smaller and smaller bits. And that's how multiplication in binary tower fields, or even in like general extension fields, is computed. Now the problem here is this gets very expensive as you climb the binary tower field, because the degree of your recursion increases once you climb up this ladder. So if I just have to give like some benchmarking numbers, so these are from actually the Benius repository, where I'm measuring the time it takes to do one base field multiplication, let's say GF2, and one multiplication in the extension field. So two elements from the extension field GF2 to the power 128, and then I compare uh, the time it takes to uh, so I just divide the time it takes to do one extension field multiplication divided by time it takes to do one base field multiplication. And you can see,
Excuse
yeah,
me, have you are you using the this ABX instructions where you have this carryless multiplication?
yes, I'm using the yeah, I'm using carryless multiplication.
Okay, okay, cool.
Yeah. So I've not written the multiplication functions themselves. I'm basically just benchmarking the carryless multiplication that is implemented in the Benius repository.
I
They
see.
have the binary tower field implementation.
Okay.
So even then, it shows us that one extension field multiplication is 4 orders of magnitude more costly than one base field multiplication if you consider the first row of this table, uh, which which is a big factor, and that sort of highlights that extension field multiplications are very expensive as compared to the base field multiplications. And if you scroll over the next two rows, what we see is as the degree of extension reduces, so by that I mean if we consider a slightly larger base field, so instead of 2 elements, if I consider 4 elements in my base field or 16 elements in my base field, um, the ratio decreases, ratio of extension multiplication divided by base field multiplication. And that's simply because the degree of extension reduces. So the degree of recursion, when you break down these larger elements, now you need to do few less recursions. So the summary of this is basically extension field multiplications are very expensive, especially in the extreme case when you consider the base field GF2 and extension field 2 to the power 128. I'll again pause for a quick moment. Okay. Sorry. Okay. So then what's the solution to make this extension field multiplication faster? The solution is we basically try to avoid extension field multiplications as much as possible, which leads to two very simple algorithms for running sum check over small characteristic fields. We have the paper online, so it's out there. And as I said, the objective is to minimize extension field multiplications or avoid extension field multiplications as much as possible. Even if that means we want to do more, we need to do more base field multiplications, that's okay. But we try to avoid um, extension field multiplications as much as possible. Now, our algorithms also generalize for usual sum check or the sum check over larger fields like BN254 or even BLS, and can speed up the prover. Our results show for BLS curve, the field from the BLS curve, we get like a 3 to 4x improvement in the prover speed, end-to-end prover speed, when the witnesses are small. So for example, if the witnesses are all less than 16 bits and your field is larger, you again get a scenario where your witness is small, but the challenges are going to be large because you sample the challenge from the large field. So our algorithms also generalizes for those cases, but the results are slightly modest. Um, a quick note on comparison with one other approach that we have mentioned in the paper in making um, in making specifically improving the runtime of some check protocol over small fields was the paper by Angus Gruen this year, which uses the technique called univariate skip, which is basically um, you try to so if we remind ourselves of the Binias profiling. Actually, let me just quickly hover back to the Binias profile picture. Yeah, if we look here, we see that the first round of sum check takes up the most of the time because um, the first round of sum check does a linear operation of size n by n, and then the next round does n by 2 and then n by 4 and so on. So what Gruen does is try to focus on the first round. If we can speed up the first round, um, that should should allow us to um, make sum check faster. So basically, I'll go back to the so by univariate skip, what he means is um, keeping, instead of having the degree of all variables in your um, sum check polynomial to be 1, uh, we we specifically set the degree of one of the variables to be large, so that when you process that variable in one of the sum check rounds, you need to do more work, but uh, for rest of those rounds, we try and keep the degree of other variables to be constant. That's the basic idea. So our approach is slightly different from Angus's approach. Um, and because, as I mentioned, he uses this larger degree for one variable, the proof size of coming out from those sum check proofs is slightly larger than the proof size that a usual multilinear sum check results in. So our technique results in slightly lower proof sizes. Um our techniques also apply to existing sum check based narcs as is, in the sense that if you use the univariate skip, you also need to slightly modify the commitment scheme to take care of the higher degree of one of the variables. Uh, but that's not the case in our protocol. You can basically just plug this in your existing sum check implementation. Uh, our techniques, one slight downside is our techniques don't they apply to a composition polynomial. By composition, let's say you have a linear combination of some multilinear polynomials. Um, we can still apply our techniques to the individual monomial terms, um, but that may lead to some memory overheads because you need to process each of those monomials separately. Um and in that case, I think Gruen's approach might be slightly better when you want to apply some check to a composition polynomial. Um, I think I should also mention that there's a couple of other papers that talk about optimizing. I think one is Ron's paper that talks about efficient evaluation of these multilinear polynomials. And there's also a paper from Kwong and Justin Thaler that talks about dealing with the equality polynomial in some check instances. Both of those work, I believe, are complementary to our work, so they should be applicable on top of our work, or our work should be applicable on top of those optimizations. Okay. So now I'll quickly uh, share a bit about what sort of performance numbers we are getting, and then we'll dive into how the math works. So we have an open source implementation, just a proof of concept in Rust, where we have also implemented the binary tower fields from Binius. Um, or specifically the binary tower field arithmetic, and then built our algorithms on top of that. So we have implemented a total of 4 algorithms. First is the naive algorithm. Second is um, second is one more variant from an old paper by Justin. And then the third and fourth algorithm is the one that we'll talk about today. Uh, So we'll quickly try and discuss what sort of results we are getting. Um, so this is a plot of the factor improvement. Um, by that I mean we are plotting the time it takes for the naive algorithm divided by the time it takes to run one of our algorithm. Uh, in this case, we are setting n equal to constant 20. This is the size, instance size of the sum check. So your polynomials would be 2 to the power 20. And the solid line is algorithm 4, which is basically the Tumcook algorithm. Um, and the dotted line is the school book algorithm. So these are the 2 new algorithms that we came up with. And we see that for degree d equal to 2. So I'm plotting the factor improvement of some check prover when you multiply two polynomials, let's say p and q, um, for of sizes 2 to the power 20 each, and then take the sum of the product polynomial. And we see that the um, the end-to-end prover time, it almost has, also I should mention the x-axis here is something called as switchover round, by which I mean that we are applying our algorithms only for the first few rounds of the sum check. Because as we saw in the Binias profiling, the first few rounds itself is the main bottleneck. And if we can compress that somehow or make it compact, that should make our sum check prover faster. So let's look at the peak, which is at round 7. So by that I mean that for the first 7 rounds, we are applying our optimized algorithms and then switching to the naive algorithm after that. So yeah, I forgot to mention this point earlier. Our algorithms also allow you to switch, only apply these optimizations for the first few rounds and then just switch back to the naive algorithm. So if you look at t equal to 7, sorry, then we see that the school book algorithm, it's about 10 times faster than the naive sum check algorithm. And the Tumcook algorithm is about 12.5 times faster than the naive algorithm. Questions? Okay. So that's why I sort of mentioned in the topic of the talk that this leads in certain configurations to a 10x faster prover. We'll take a look at one more configuration, which is for slightly larger degree. So if we take degree d equal to 3, so you have 3 polynomials being multiplied, and you apply both of our algorithms, we see that the performance degrades slightly, in the sense that now your factor improvement is less as compared to when it was for degree d equal to 2. But you still see that the Tumcook algorithm gives about a 7 or 7.5 times improvement over the naive algorithm. The also one slight differentiation for degree d equal to 3 is the peaks of the two algorithms is different. So if you're using algorithm 3, you should, or the school book algorithm, you should probably switch after round 4. But if you use the Tumcook algorithm, you should switch after round 5. Okay, so basically, the both of our algorithms show some promising improvements over the naive algorithm uh, when we run this when we run the sum check over the base field being GF2 and the extension field being GF2 to the power 128. Now, how do we so the next thing that we'll discuss is how do we achieve this, or what's the mathematical formulation. Um, so as I said, I'll describe only the product sum check case, where you want to prove multilinear extension, uh, product of multilinear extensions. So let's say you have like d polynomials that you want to multiply. The sum check round polynomial in round I looks something like this. So now R1 to Ri minus 1 is basically the challenges that we have from the previous rounds. And these challenges are from the extension field. So these challenges are very large numbers. In this case, they are like 128-bit numbers. So now if we just plug in the product polynomial, um, we'll have a product of these P1 to PD polynomials. Now these polynomial evaluations on these challenges are extension field elements, right? Because as soon as you substitute these challenges or evaluate these polynomials on bunch of challenges, you enter the extension field domain. So therefore, our original objective was to minimize these product of extension field elements. So we'll see how we manage to do that. It's fairly straightforward, and I'll try to just give a glimpse of how the two algorithms work. So one thing to notice is this is not a product of random extension field elements. Of course, it has randomness because you have these challenges R1 to Ri minus 1, but because our polynomials are multilinear extensions, we have a nice structure of um, uh, we have a nice structure in which we can separate the witness terms and the challenge terms. So challenge terms are all extension field elements. And to compute these challenge terms, you cannot avoid doing extension field multiplications, but you can basically segregate all the challenge terms and the witness terms. So now witness terms, the one you see on the right, are all from the base field. So they are like 0, 1 in this particular example. But the challenges are 128-bit elements. Now, if so this is um, one polynomial, like one multilinear polynomial. We are interested in the product of d such multilinear polynomials. So the question is, can we still keep this segregation between the challenge terms and the witness terms even when we multiply such multilinear polynomials? And the simple answer is yes, we can do that. So if we let's look at the simplest possible example. So let's say we are in round 2. Um, uh, so the round polynomial that you're computing is you need to substitute the first challenge R1 in the two polynomials. Let's say P and Q are the two polynomials. So once you substitute these challenges, you as I mentioned, you can write them as a linear combination because we are only dealing with multilinear polynomials. So the red part and the green part is the witness terms, and the gray part is the challenge terms. So now if you multiply P and Q, you're going to get 4 terms. So I do the naive multiplication. First, red part multiplies with red, red multiplies with green, green multiplies with red, and again, green multiplies with green. Simple school book multiplication. And therefore, what you observe is you are still able to maintain this segregation between the challenge terms and the witness terms, even when you multiply these multilinear polynomials. And that's the key observation that we had. I'll pause for a quick moment if anyone wants to interrupt with questions. If not, then
Hi. Yeah.
yeah.
I thank you for the introduction. I'm wondering, what's the relationship of this technique with increasing the degree of variables. Like if I if I group the first several variables and then increase the degree of the first polynomial, I feel like this is a similar approach of optimization. Do you have any idea what's the relationship between this technique and the technique of grouping the first several variables?
Right. So correct me if I understand your question. So you're saying after the first round, let's say I sample two challenges, R1 and R2, and substitute them. So I basically send like process two variables at a time, right?
Yeah.
I think even in that case, our algorithm would still apply, because essentially what our algorithm is just simply how to deal with multiplication when you have a bunch of large elements being multiplied with small elements. So we haven't done a comparison with that approach, and uh, I think probably we could like uh, give it a bit more thought, but we haven't already like compared with that approach.
Yeah, gotcha. No problem. Thank you.
Cool. Yeah. But good idea. I think it's worth trying what happens if we process more variables in a given round. Okay, so coming back to
I
this,
think,
yeah,
I think if you do this in all rounds, this will increase the proof size.
yeah, it does increase the proof size. Yeah, cool. Okay, so coming back to this linear combination, so in case of two polynomials, it's very simple, P and Q. If we have D polynomials, let's say of this form. So 1 minus x and x are the two like challenge terms or like larger terms, and alpha j, beta j are the coefficients or the witness terms. So we'll take the case of this multiplication of just linear polynomials in x. So simple school book multiplication would allow us to multiply these D polynomials by again using the same strategy of segregating the coefficient products and segregating the variable products. So all you need to do is process all of your challenge terms separately or x terms separately and process all of your coefficient products separately. And then sort of format them into two vectors and just take the inner product. And that should give you your evaluation on X. Now, and that's nothing but our third algorithm. What's the cost of this algorithm is if in this particular case to compute one of these coefficient products, we'll need D minus 1 multiplications, base field multiplications. So BB stands for base field multiplied by base field. And then we need to do 2 to the power D of such coefficient products. So that's the total number of base field multiplications that we require. Also, it's not just the multiplications, but the amount of memory that you need to store is 2 to the power D. Right? Because you need to store all these coefficient products as a vector. So there's also cost in terms of memory. So the downside or like what you pay is in terms of memory when you use this school book multiplication as compared to the naive algorithm. We'll sort of touch upon what's the practical difference that we observe in memory in the last slide. But for now, By using school book multiplication, you can basically compute product of d linear polynomials by separating the challenge terms and the witness terms. Now, if we want to do this product efficiently, let's say we want a slightly more efficient way to multiply d polynomials. And the obvious answer to that is just doing FFT, right? We are used to multiplying polynomials in their evaluation domain, which gives us which gives, so school book algorithm typically costs you quadratic time. If you just simply talk in terms of polynomial multiplication, but FFT allows you to do it in n log n. And the basic idea of doing an FFT is just transform all the polynomials in their evaluation domain, then just do pointwise multiplication, and then again take an inverse FFT and convert it back to coefficient form if you like. And that's the exact same idea that we try to do. So, so the only difference here is instead of doing an FFT, we'll do something much simpler. So notice that the degree of this f polynomial is d, because we are just multiplying d polynomials. So the idea is you just evaluate each of the constituent polynomials on d+1 points, just compute pointwise multiplications, and then just take some kind of inverse to go back to your coefficient domain. In this case, it's much more easier because the points that we choose, the evaluation points, it's our choice. So we can choose points such that computing this evaluations would not cost us much. In fact, it's a requirement, or it's an assumption that we are making, that evaluation must cost you negligible. As if you compare like the cost of evaluating versus the cost of doing extension field multiplication. So therefore, you choose these E0 to ED points such that you get minimum base field multiplications while computing the evaluations. Now, as I said, like we just take the inverse of this evaluation matrix and you get back your coefficient form. So the actual like matrix operation here is not that important, but what this allows you to do is the total multiplication cost in the base field reduces. So in the previous slide, we had d-1 times 2 to the power d, but in this slide, we have d-1 multiplied by d+1. And that's the main advantage of the fourth algorithm, or the second algorithm in this presentation, especially in terms of memory. And we'll see, as promised, we'll see how much of a difference it makes in memory. I'm going to skip over some of the math in few of the next slides, but this slide is just basically summary of the two types of multiplication. So if you use school book multiplication, you have d-1 times 2 to the power d. If you use Sumcheck, so this is actually a generalization of the Sumcheck method that's famous as a low-level multiplication algorithm, which costs you d-1 time d+1 base field multiplications. And also both of these are the numbers that you require. It's the memory requirement of the two of our algorithms. What we show in the paper is that both of these techniques fit into like a nice format of this Sumcheck round polynomials, where you can basically generalize both of these algorithms as one single equation. Now, going back to Sumcheck, what we saw in the previous slide is just how do we multiply d-linear polynomials. But in our case, we may not have linear polynomials because you may have more than one variables like r1, r2 up to ri minus 1. So I'll skip over this slide and just come to the conclusion, which is you can basically plug the idea of doing d-linear polynomials in Sumcheck, but you need to do it repetitively for each variable. And what do I mean by that is when you look at the Sumcheck expression, product of d polynomials, let's say I only process the first variable. So that would, so I can just expand it using the expression that I had for computing product of d linear polynomials. That leads to a sum of like a certain sum, and then internally you have this product here. Again, you see the product here also consists of, is essentially a product of d linear polynomials, but now in the variable r2. So now you process the variable r2, and you keep doing that until you have processed all the challenges basically. And eventually what you'll realize is what you get as product is everything from the witness. It's basically a product of all witnesses, which is much cheaper to compute. And then you just keep doing this inner product with different variants of your challenge vector. So for R1, you'll have vector. There's a typo here, right? It should have been R2, this should have been R3, and so on. So that's how you sort of plug our technique of product of linear polynomials into Sumcheck repetitively, and that gives you both of our algorithms. The only difference would be in this capital M, where M is 2 to the power d in case of school book multiplication, and M is just d plus 1 in case of the Domb method. Okay, so the very last point is why Domb when even the dotted line, which is the school book algorithm, is giving us good enough results. So there's two reasons. One is memory. There's a significantly less memory requirement by the Domb algorithm as compared to the school book algorithm. In this particular example, you need just 0.6 MB memory in Domb versus 84 MB in school book, and this 84 MB increases exponentially as you increase t or as you increase the degree. So in memory constrained system, Domb algorithm is the best to use. And second reason is, of course, performance, which you can see the Domb algorithm is always better than the school book algorithm in terms of performance. Sometimes it may be 2 times faster than school book, sometimes it may be 3 times, sometimes it may be just, let's say, 1.4, 1.5 times faster. That depends on your configuration. But that's basically it. So that's why the fourth algorithm, the main advantage of it is the less memory requirement. And now I'll stop for questions.
I guess I'm very interested in this memory efficiency. Like, do you have a comparison? Like, how many X do you get in terms of memory?
Yes, we do have a plot in our paper. Let me just quickly open the plot. There you go. So if you look at the left plot, it's the memory requirement of the two algorithms. Algorithm 3 is the school book, and algorithm 4 is the Tumcook. So you can see there's a 3 orders of magnitude difference if you compare at after you if your switchover round is equal to 10, and then the difference naturally grows if your switchover round is larger.
I see.
So there is significant difference. I think we also had a number here. I think for the switchover, if the switchover round is 10, then algorithm 3 requires 4.2 GB of memory, but algorithm 4 requires just 4 MB. So it does make a difference if you really are concerned about memory or if you're doing client-side proving.
Got it. Got it. Well, that's very significant because we have some application where we want to try to prove some checking mobile phone, and
Right.
in most cases they're really constrained with the memory. And
Yeah.
okay,
Yeah.
cool.
So typically, like I think Justin had released this algorithm 3 by himself, and we realized that okay, we are getting a good speed up, but then memory was a big concern because even we were trying to use the some check in some memory constrained devices.
Right.
So then we started sort of working back and trying to see if we can come up with a more memory efficient version, and that's how we got algorithm 4.
Okay, cool. Thanks. Does anyone else have questions? But right now we're at time, so if there's no questions, thank you again for the talk, and that'll be all for today. See you soon.
Thank you very much.
Thank you.
Thank you.